This is usually the first thing a frontier lab asks you about attention. The 3 learned projections, and how you answer it tells them right away whether you actually get this or you just memorize some letters. Okay, picture a little dating app, but for words. Every word in your sentence is on it, and each one is trying to figure out who else in the room is worth paying attention to. So each word writes a query. That is its little dating profile of what it is looking for right now. Like, I am a verb, I could really use a subject around here. And every word also puts out a key. That is the flip side, what it is advertising about itself. When one word's query lines up nicely with another word's key, that is a match, and that is a high attention score. Then there is the value, and this is the one people forget. The query and the key just decide who talks to who. The value is the actual message that gets passed along once they have matched. It is the content, kept totally separate from the matchmaking. And here is the neat part. All 3 come from the exact same word. You take the input embedding and push it through 3 different learned weight matrices, one for the queries, one for the keys, one for the values. Same word, 3 different jobs. Now here is where most people quietly lose the room. They say, oh yeah, Q, K, and V, and then they just stop. 3 letters, but naming them is not the same as understanding them, and the interviewer can feel that gap instantly. The answer that moves you forward says what each one does. The queries and the keys decide where to attend. That is the scores. The values are the content that actually gets mixed together. That one extra sentence is the whole difference. So go wire up all 3 projections by hand and watch a word go find its match. Once you have built it, you will never confuse the value for the key again. The free notebook is in the bio. This is the follow-up question that catches a lot of people off guard. Why do we divide the attention scores by the square root of the key dimension? There is one little term in the formula, and they want to know if you understand why it is even there. Think of it as a volume knob on the scores. Before anything else happens, you want the numbers going into the next step to be calm and reasonable, not blown out and screaming. That knob is the whole job of this term. Remember, a raw score is the dot product of a query and a key. You multiply them piece by piece and add it all up. So the more pieces there are, the bigger that sum tends to get. And that is exactly where it goes wrong. When the key dimension is large, you are adding up a lot of terms, so those dot products grow huge. Now you feed those giant numbers into a softmax, and it saturates. It slams almost all the weight onto one word and basically ignores the rest. And a saturated softmax is a quiet disaster, because out in that flat region the gradients go almost to 0. So the model stops getting a useful signal, and learning just grinds to a halt. So the fix is to divide every score by the square root of the key dimension. As the dimension grows, you scale the numbers back down by just the right amount, and the scores stay in a sane range no matter how big the model gets. And the square root is not random. The spread of those dot products grows with the dimension, and dividing by the square root pulls the variance back to about 1. That is the precise number that keeps the softmax in its healthy, sensitive zone. So the shallow answer is O to normalize it. That is not wrong, but it says nothing. The answer that lands names the actual failure. Large key dimension grows the dot products, the softmax saturates, the gradients vanish, and dividing by the square root holds the variance near 1. So go run it both ways yourself, with the scaling and without, and watch the gradients flatline when you take it out. That is the moment it really lands. The free notebook is in the bio. Here's one you'll get in a Frontier Lab interview. Can you write out the full-scale dot product attention formula from memory? Most people freeze, but it's really just 3 moves. Picture a group chat. Every word in your sentence wants to know one thing. Who else in here actually matters to me? So each word sends out a question, and every other word answers with a key. When a question and a key line up, you get a high score. That score is just the dot product of the queries and the keys. Now here's the part they're really listening for. If you let those scores run wild, they blow up, the softmax saturates, and your gradients basically vanish. So you divide by the square root of the key dimension. Think of it as turning down the volume so nobody is screaming. Then a softmax turns those scores into clean weights that add up to 1. And you use those weights to blend the values, the actual information each word is carrying. And that is it, that is attention, the whole engine right there. Here's what actually gets you the offer though. Anyone can recite the formula. The ones who get hired can explain the why you turn the volume down, and why the values stay separate from the queries and the keys. So don't just memorize it, go build it yourself from scratch. The free notebook is in the bio. So attention lets every word look around the sentence. Here is the follow-up that trips people up. Why do the real models run a whole bunch of those at once? Think of reading a sentence with a group of friends instead of alone. One tracks the grammar, another follows who did what to whom, someone else feels out the tone. A single attention head only makes one kind of comparison at a time, one lens, but language is doing 5 things at once, so one lens leaves a lot on the table. So instead of one giant attention over the full model width, you slice that width into a handful of chunks. Each chunk is a head, with its own projections for the queries, keys, and values. Every head runs that same attention move inside its own smaller space, all at once. So each is free to specialize. One chases grammar, another tracks who the word refers to. Then you glue those head outputs back together and run one more projection to mix them. That mix is where the model decides how much each point of view mattered. And that is multi-head attention. Many points of view gathered at the same time in one pass. Same total cost, way richer picture. Now the tempting miss is, more heads just means more capacity. But the answer that gets the offer is sharper. You split the same budget so each head attends to a different subspace at once. Variety of attention, not more compute. So do not just memorize the words. Go split the heads yourself and watch them specialize. The free notebook is in the bio. Here is a question that quietly decides a lot of interviews. Why does feeding a model a really long document get so brutally expensive, so fast? One number is the reason. Picture a party where every guest shakes hands with every other guest. Cozy gathering, no problem. But watch what happens as the room fills up. Double the guests and you do not get double the handshakes. You get 4 times as many. 10 times the guests is 100 times the handshakes. It runs away from you. And that is exactly what attention does. Every word compares itself against every other word to figure out who matters. That is the handshake. Those comparisons come from the dot product of the queries and the keys, landing in a big grid of scores. 1,000 words means a grid 1,000 by 1,000. 1,000,000 scores. So the cost grows with the square of the sequence length. That is what people mean by quadratic. The length gets multiplied by itself, and that is the part that hurts. And that is the bottleneck. It is why a model cannot just casually swallow an entire book. That one squared term is the wall everybody is trying to climb. Now the shallow answer is, A, it is just slow on long inputs. That is a shrug. The answer that gets you hired names the culprit. The score grid is sequence length by sequence length, so cost scales with length squared. And that fact is what every long context method is built to beat. So go build attention from scratch and watch that grid blow up as you grow the input. Feel the wall yourself. The free notebook is in the bio. Real puzzle. A model writes one word at a time, but during training it sees the whole sentence at once. So how do you stop it from peeking at the answer it is supposed to guess? Imagine a fill-in-the-blank test where the answer key is printed right there on the page. You would not learn, you would just copy. The model has the same temptation. Remember, attention lets every word look at every other word, both directions. Great for understanding. But for writing the next word, the future is sitting right there. So we make one rule. When a word decides what comes next, it can only look at itself and the words behind it. It reads the past, never the future. And the move is almost sneaky. In that grid of scores, every spot pointing at a future word gets shoved down to negative infinity. You are blacking out the answer key with a marker. Then the softmax turns those scores into listening weights, and anything at negative infinity gets a weight of basically 0. So the future contributes nothing. And that is causal masking. You blank out the upper half of the score grid before the softmax, so each position only attends to itself and the past. Now the shallow answer is just so the model does not peak. That is the vibe, not the mechanism. The higher level answer names it. You set the future scores to negative infinity before the softmax, so each position attends only to itself and earlier ones. And only looking back is what makes generation autoregressive. So go build the mask yourself and watch the model suddenly stop peaking. Wildly satisfying. The free notebook is in the bio. This one shows up the second you serve these models for real. Grouped query attention. And you cannot explain it until you know what was actually hurting. When a model generates, it saves the keys and values for every word it has seen to avoid redoing the work. That pile is the key value cache, and on long chats it eats your memory. Think of a study group. Classic multi-head attention is like every person keeping their own full set of notes. Thorough, but a lot of duplicated paper lying around. The other extreme is multi-query attention, where the whole group shares one set of notes. Super light on memory, but with everyone on one page, you lose that perspective magic. Grouped query attention splits the difference. You sort the heads into small groups, each group sharing one set of keys and values. A few shared notebooks, not one, not 100. And that is the payoff. Far fewer keys and values to store, so the cache shrinks hard, but you keep enough groups that quality barely drops. Most of the smarts, a fraction of the memory. And this is not a whiteboard idea. It is in big open models you have heard of, like the 70 billion parameter Llama 2. It is how they keep serving fast. So the shallow answer is, oh, it is just a faster attention. That misses the point. The answer that lands the offer is clean. Query heads share one set of keys and values per group, shrinking the key value cache, the real inference bottleneck, while keeping most of the quality. So go build all three yourself and watch the cache shrink as you group the heads. That is when it clicks. The free notebook is in the bio. Okay, weird fact to start. Raw attention has zero sense of order. Shuffle the words in your sentence and it would give the exact same answer. So how does the original transformer know the first word from the last? That's today. Here's the issue. Attention looks at every word at once and asks who relates to who. Great for meaning, but it treats your sentence like a bag of words tossed on a table. Dog bites man and man bites dog look identical. We have to hand it the positions. And the original idea is honestly kind of beautiful. Think of a row of clocks, some spinning fast, some slow. For each position you read off where all the hands point. Fast clocks tell you fine detail, slow clocks tell you roughly where you are. Together they fingerprint the spot. Those clock hands are just sine and cosine waves. For each position you take a sine and a cosine, and every dimension uses a different wavelength, set by 10,000 raised to a fraction across the model's width. Low dimensions wiggle fast, high dimensions crawl. A whole spectrum of waves. And why waves instead of just counting 1, 2, 3? Because waves are smooth and they never run out. The pattern keeps going past any length you trained on, and nearby positions get similar codes. The model can feel relative distance, not just absolute spot. And that's it. You add this little bundle of waves straight onto each word's vector before attention ever sees it. Now order is baked in. The model can finally tell the first word from the 5th from the 500th. Now the honest update. Almost nobody adds these waves anymore. Modern models use rotary position embeddings, ROP, which rotate the queries and keys instead of adding anything. But it grew straight out of this same idea, encode position with rotations. And here's the offer-getter. Anyone can recite sine on the even dimensions, cosine on the odd. The hired answer says why waves at all. They're smooth, they extend past your training length, and they let the model read relative distance. That's the part most people skip. So go plot these waves yourself and watch each position turn into its own little fingerprint. It stops being a formula and starts making sense. The free notebook's in the bio. So this is the position scheme living inside basically every model you actually use today. ROP, rotary position embeddings. And you can't really explain it until you see what it does differently. So let's get it. Quick recap. The old way bolted a position code onto each word before attention. It worked, but it's a bit awkward. You're stapling where to the what, and it doesn't naturally handle going past the lengths you trained on. ROP takes a cleaner swing. Here's the whole idea in one move. Instead of adding anything, you rotate. Picture each word's vector as an arrow. ROP spins that arrow by an angle that depends on its position. Word 1 gets a tiny turn, word 50 a bigger turn. Position becomes an angle. And it does this to the queries and the keys, the two things attention compares. It chops each vector into little pairs of numbers and spins each pair like a dial on a flat, two-dimensional plane. A rotation. Nothing added, nothing learned. Just a turn that grows with position. Now here's where it pays off. When attention takes the dot product of a query and a key, those two rotations combine. And the math works out so it only depends on the difference between their positions. How far apart they are, not where they sit. Relative distance falls right out. And that one property buys you a lot. Attention naturally fades for words far apart, which is usually what you want. There are no extra parameters to learn, and because it's pure geometry, it extends to long contexts. Stretch the angles a bit with NTK-aware scaling and it keeps holding up. And that's it, that's ROP. You spin the queries and keys by their position, and the comparison automatically reads relative distance. That's why the long context, open models you've heard of basically all run it now. And here's the offer-getter. Anyone can say ROP rotates the queries and keys. The hired answer says why that's clever. The rotations combine in the dot product so attention only sees relative distance. It costs no parameters, and it scales to long contexts. Say that and they know you've actually used it. So go rotate a couple of vectors yourself and watch their dot product depend only on the gap between them. That's the moment it clicks. The free notebook's in the bio. Everyone obsesses over attention, but half the parameters in a transformer block live somewhere else in the feed-forward network. They'll ask what it actually does, and a lot of people freeze. Let's not be those people. Here's the mental split. Attention is the part where words talk to each other and share context. The feed-forward network is the quiet part right after, where the model sits with each word on its own and actually thinks about it. Mixing, then processing. And the shape of it is satisfying. Take each word's vector, blow it up into a much wider space, do some nonlinear thinking out there where there's room, then squeeze it back down to size. Expand, ponder, compress. So concretely, 3 moves. First matrix projects the word up from the model width to about 4 times wider. Then a nonlinear activation bends it, which is where the real pattern finding happens. Then a second matrix brings it back down. Up, bend, down. And why bother going wide? Because that fat middle layer is where a ton of the model's actual knowledge lives. More width means more room to store little patterns and facts. It's the memory and the reasoning scratchpad of the block, all in one. Now the modern upgrade worth naming. It's called Swiglu and it adds a gate. You run 2 projections side by side. One goes through a smooth activation, the silu, and the other acts like a volume knob, multiplied in element by element. The gate decides how much of each signal passes through. And here's the neat accounting. That gate means 3 matrices instead of 2, which would normally cost more. So they shrink the middle to about 2/3 of the usual width. Same parameter budget, better results. You get the gating for free. And here's the offer getter. Anyone can say it's 2 linear layers with an activation in the middle. The hired answer explains the wide middle is where knowledge lives, and that Swiglu adds a gate while trimming the inner width to 2/3 to keep the parameter count fair. That's the depth they want. So go build both the plain feed-forward and the gated Swiglu and watch the difference for yourself. It's a tiny block doing a lot of the work. The free notebook's in the bio. This one looks like a nitpick and it's quietly huge. In a transformer block, do you normalize before the layer or after it? That tiny choice is the difference between a deep model that trains smoothly and one that just blows up. Let's get it. Quick grounding. Normalizing just takes a vector and rescales it back to a sane, steady range, so the numbers don't drift huge or tiny as they flow through the network. Think of it as a thermostat keeping things comfortable. The question is only where you put the thermostat. And you need one more piece, the residual connection. Every block has a shortcut that carries the input straight around the layer and adds it back. Picture a highway running through the whole model, with each layer as an exit ramp that merges back on. Keeping that highway clear is everything. The original transformer did post-norm. You do the layer, add the shortcut back, and then normalize the whole sum. Problem is, you're putting a thermostat directly on the highway. Every single layer squeezes that signal, and stack enough of them and the gradients choke on the way back. Deep models get really hard to train. Pre-norm flips it. You normalize first, feed that into the layer, then add the result back onto the untouched shortcut. Now the highway stays clean end to end. You only normalize the stuff merging on, never the through traffic. The signal flows all the way down without getting strangled. And that's the payoff. With that clean shortcut, gradients flow freely from the top of the model to the bottom. You can stack way more layers and training just stays stable. That's why almost every modern large model is pre-norm. It scales. And one detail to drop so they know you're current. Modern models pair pre-norm with RMSNorm, a lighter, cheaper normalizer. So the full modern recipe is normalized before each layer, using RMSNorm. That's the combo running in the big open models today. And here's the offer getter. Anyone can say pre-norm normalizes before, post-norm after. The hired answer names why it matters. Pre-norm keeps the residual path clean so gradients flow through deep stacks without choking, which is why it won. That why is the whole point. So go build both, stack the layers deep and watch post-norm wobble while pre-norm holds steady. That's when it really lands. The free notebook's in the bio. So here's a quiet little change that almost every modern model made. They dropped the classic normalizer, LayerNorm, for something leaner called RMSNorm. They'll ask what it is and why. And the answer is genuinely simple, which is the fun part. First, why normalize at all? As numbers flow through a deep network, they tend to drift, getting huge in some spots, tiny in others, and that wrecks training. Normalizing pulls each vector back to a steady, comfortable scale. It's the stabilizer that keeps the whole thing trainable. Old-school LayerNorm does two things. First, it recenters. It finds the average of the vector and subtracts it so everything sits around 0. Then it rescales by the spread. 2 steps, center and scale. And here's the question someone finally asked. Do we really need that centering step? Turns out mostly not. RMSNorm throws out the recentering entirely. It just measures the root mean square of the vector, basically its typical magnitude, and divides by that. No averaging, no subtracting. 1 step instead of 2. Then a learned scale on top, same as before. And that's the payoff. Fewer operations means it runs about 10 to 15% faster, and you do this in every layer so it adds up across the whole model. And the kicker, in practice the quality is just as good. You dropped a step and lost nothing. And there's a deeper lesson here they love. It told us the centering was mostly doing nothing all along. The real benefit of normalizing was the rescaling. Someone questioned a step everyone assumed was necessary, and the simpler thing won. And this isn't a fringe idea. It's running in the big open models you've heard of, the Llama family, Mistral, basically the modern standard. So when you name RMSNorm, you're naming what's actually shipping today. And here's the offer-getter. Anyone can say RMSNorm is faster. The hired answer says exactly why. It drops the mean centering step, keeps only the rescaling by the root mean square, runs 10 to 15% quicker, and matches LayerNorm on quality. Naming the dropped step is the tell. So go code both, line them up, and watch RMSNorm match LayerNorm with 1 less step. Simple beats fancy more often than you'd think. The free notebook's in the bio.